Okay, let's begin a little review before we look at homework 12.1, just some basic concepts. Um, we're given mass fractions and we're trying to find mole fractions. So to start with, the mass fraction would just be the mass for component I. If we have several gases, we'll just refer to each one as mass 1, mass 2, mass 3. So not knowing which one, we'll just put Mi and then the sum of the mass for each component. The mole fraction is the same thing except with the number of moles for component I and the sum of all the moles for each gas. And then also the molecular weight for any particular gas would be the mass of that gas over the number of moles. So that gives us a few tools to start with. You'll notice that if you sum up all the mass fractions, you'll get 1. If you sum up all the mole fractions, you'll get 1. The other concept we have is that the molecular weight for the mixture, if we want to use, say, the ideal gas law, such as PV equals MRT, where we note that R equals the universal gas constant divided by the molecular weight. If we're going to use the molecular weight, we have to use the molecular weight for the mixture if we're going to treat the mixture as an ideal gas. So we need to come up with some way of getting the total mass. So the molecular weight for the mixture, this one that we're going to use in this equation, is going to be sum of all masses of each gas divided by total, or the sum of all the moles. So the total mass over total moles. So let's see if we can come up with a way to find that from mass fractions. So we want the mixture molecular weight, this last thing that I have here. And in this problem, we have different gases. The gases are CO2. The second gas listed is N2 and O2. One of the things we're going to need, if we look in the tables, we'll find molecular weights for each of these. And if we go to table A1 in the appendix, you can find each of these. Let me turn there. And you'll see that the first column is the substance or the gas, the second is the chemical formula, and the third is the molar mass or molecular weight. So the first one we're looking for is CO2, which is carbon dioxide, which is 44.01. And the units of this could be expressed as kilogram per kilomole. Could also be pound per pound mole or gram per mole. Be the same number for any of those sets of units because the definition of a mole and a kilomole is such that we get the same number in each case. The next gas is nitrogen, and if we look for nitrogen, find 28.01, and we look up oxygen, and we get 32.00. So we've got our three gases, and some others that we're going to use in the next problem we can put for now, at least one other one that we'll need. Hydrogen, 2.016. So that's for another problem, just so that we have it here on the board. All right, and Now we need to know the mass fraction of each. So, or well, we have the mass fraction of each given in the problem. For this problem, mass fraction was 0.1237 for the CO2 carbon dioxide, 0.728 for the nitrogen, and 0.0787 for the oxygen. And if we add these up, they should all add to 1. So we've got about 73 plus 0.12, so another 12 and another 8. So let's see. We do have H2O. Wasn't adding up. So let's add one more here. H2O. Of course, we have no hydrogen in this problem, and we look up hydrogen or water, H2O, we get 18.02. So it was a good thing I double checked for those to all add up to 1. They didn't quite, and we have 0.0696 for H2O. And in this case, no hydrogen. All right, so what we're after is first the mixture molecular weight, which is this term right here. So we have mass fractions, not mass. So we're going to have to figure out a way to, if we want to use this expression, come up with a total mass. So one approach is to consider that the mass of each component is the same as the mass fraction. So if this was 0.1237, 0.728, 0.0787, 0, and 0.0696, then that would be a solution. Now you'd be right in saying, well, but how do we know that that is the mass? We don't, but the ratio of those masses would have to equal that to give us those mass fractions. So you could multiply those times 10, you could multiply them times 100, you could multiply them times any constant. So those would be the right values if, in fact, I multiplied them by some constant. So let's say times some constant C. And then if I sum those all up, it would be all of those added together times C, and then when I put them into the equation for mass fraction, I would have the total mass having a C in it, and the numerator would have a C in it, and the C's would cancel, and I would get those mass fractions. So I could at least say that they're the same except times some constant. Right, so I'm still after, though, the total mixture mass, and then I need to find the number of moles. The number of moles is not hard to find. If we use this expression, so Ni equals Mi over the molecular weight for component I. So I can make a column that's Ni, and if I do that, I'll have Mi divided by the molecular weight. So I'm going to have 0.1237 C divided by 4401. And likewise do that for each. And so 0.728 times C over 28.01, 0.0787 times C over 32, and 0.0696 times C over 18.02. Now if I sum all those up, and I sum all these up, then I can put those values into my expression for mixture of molecular weight. And if I do that, in this case, I end up with 29.61. And if I calculate each one here, let me do that. Let me pause it for a minute while I do that. All right, and so I did the numbers. It's always good to check your work because, in fact, this is not the answer. So let's calculate this and find out what the answer is. So when I sum this up for mixture molecular weight, of course, since the mass fractions all add up to 1, then this is going to also add up to 1 but times C. So this just equals C. And then the the moles add up to 0.035123. Of course, times C. So now when I put C and 0.035123, I get C divided by 0.035123 C. Now we find out, well, C didn't matter, so that constant didn't really matter. So what I learned, and about when I do that, then this is 1 over that, which 1 over 0.035123 is 28.47. Also over here I said I divided by 18 point, should be 18.02. Okay, so what do I learn from this? So I could, if I'm trying to find the mixture molecular weight, not worry about this C. And even though this is not the mass, it's the mass fraction, so what I'm doing then is using the mass fraction to calculate the mixture molecular weight, and then I'm dividing the mass fraction by the number of moles. So in fact, this number right here, if I take 1 over that, is the mixture molecular weight. So what I learned from all this is that in general, 1 over, and then what is that? That would have been the mass fraction of I divided by the molecular weight or molar mass of I, and then I summed all those up in the denominator. Let me write that a little more clearly. So mixture molecular weight is 1 over the summation of MFI over MI. All right, and there's some other elements in question 1, the total mass of the mixture, the mole fraction of CO2, the mole fraction of N2, O2, and H2O. So let's address a couple of those. So now that I have the mixture molecular weight, I can find the gas constant and the total mass of the mixture. I'm given the temperature of the mixture, the pressure of the mixture, the volume of the mixture, and I just found the gas constant of the mixture. So now I can solve for the mass. So the mass equals P of the mixture, V of the mixture over gas constant that I just found times the temperature of the mixture, where R equals the universal gas constant over the mixture molecular weight. and that will give me the mass of the mixture. Okay, then we have four more parts left, which is the mole fraction. So the mole fraction would be the moles over the total number of moles. So if we come back to this part, we have this thing that I called Ni. If I multiplied it by C and then divided it by the total number of moles, so we have Ni over summation Ni. And then if I said, well, I'll divide Ni by some constant, let's say that constant is C, then the numbers that I actually used here can be used in this equation. And so ultimately then I have yi equals, and remember this was this first term here was the mass fraction I divided by the molecular weight. So I have MFI over Mi. That's what this first term here was, of course, with the C in it, but the C didn't matter because it's in the numerator and the denominator. And then divided by summation of MFI over Mi. So now we have, if we have mass fractions, we can find mole fractions. The second problem is exactly the same one, but it's in reverse order. So I'll talk about that a little bit, but I'll let you do most of the work now.